Okay, it's 12:35, so let's begin here. Can everyone hear me and can everyone see my document camera?
Yep.
Okay, thank you. So I just want to sort of review where we got to last day, because it's a long time ago. We're talking about electrolytes, and we were reviewing the factors that influence lithium-ion conductivity and lithium-ion diffusivity in non-aqueous electrolytes. And we learned that normally the conductivity increases with lithium concentration in the electrolyte just because you have more charge carriers up to a certain point, when the viscosity of the electrolyte starts to become very much greater. And that's because as the salt dissolves in the electrolyte, the more and more salt increases the viscosity, and then the conductivity decreases. So these two factors are always present, and sometimes you have ion pairing occurring, which reduces the number of charge carriers, or pore dissociation, which is equivalent to an ion pair. And this occurs sometimes. We'll talk about this later. So I want to go back to the PowerPoint now and continue from where we were. Okay, so you should be able to see my PowerPoint now, I believe. Is that true?
Yep.
Okay, I'm making it full screen. Yeah, so I think we got this far, and maybe we started talking about this slide, which was the fact that if you want to have lithium-ion cells that can operate at high current density, which leads to a high charge rate or discharge rate, you have to use electrolytes with very high conductivity. So here's an example of a NMC graphite cell with fairly thick electrodes. It's being charged at 1C, that's okay. But at 1.5C, one of the pair cells starts to show capacity loss, and by a 2C charge, they're both showing dramatic capacity loss, and this is because of lithium plating taking place at the negative electrode surface, because the overvoltage just gets too large. So you have to develop electrolytes with better transport properties, and there's not too many things at your disposal, really. The factors that influence lithium-ion diffusivity, the concentration, and the viscosity. So really you're faced with lowering the viscosity of the electrolyte, basically, is what you have to do. And this is where solvents like esters come into play. So if you take a look at EMC, ethyl methyl carbonate, its viscosity is 0.65 centipoise at room temperature. So just to put this into perspective, ethylene carbonate at its melting point of around 39 degrees C has a viscosity over 2.5 centipoise, so EMC is much lower. And then DMC, dimethyl carbonate, is even lower. And if you want to find solvents that are compatible with lithium-ion cells, at least to some degree, you can use these esters, methyl acetate, ethyl acetate, methyl butyrate, and methyl propionate. And of these, methyl acetate has by far the lowest viscosity. And it also is, of these, the most compatible, actually, with lithium-ion cells. So that's turns out to be lucky. And if you look at the chemical structures of these things, like look at dimethyl carbonate and look at methyl acetate, they just differ by one oxygen atom. You can see this oxygen, it's just gone in methyl acetate. So the two chemicals are very similar, and you would expect the reactivity with lithiated graphite to be similar, and to first order it more or less is. So let's take a look at the you know, the benefits that things like acetates bring to the situation. So yeah, you might wonder how viscosity is measured. Eric Logan is an expert on measuring electrolyte viscosity. If you ever want to measure some, he can help you do it. We use these capillary viscometers. So it's a glass tube with a relatively large diameter at the top, and then there's a bulb, and at the bottom there's a capillary tube, narrow diameter. What you do is you fill the liquid up to a red line at the point A, and then you just let it drain under the influence of gravity until the fluid goes down to the point B, and you measure that time. And the greater the viscosity, the longer that time is. So this gets to be incredibly tedious, especially if you want to do it by as a function of temperature. So these viscometers, which we have in our lab, not shown in this panel, is a reservoir at the bottom where the fluid flows into, and then you can, with compressed argon, you can force the fluid back up. So Luc Beaulieu, who's a professor at Memorial University of Newfoundland, spent a sabbatical with us about 3 years ago, or maybe 4 years ago, where he automated these viscosity measurements. So he set it up so that the viscometer was placed in a temperature-controlled box, and a computer said, okay, drive the fluid back up with compressed argon. And when the fluid column hit the point A, a valve opened and allowed the fluid to drain back down, and a webcam captured the location of the meniscus as it went down and timed the time it took to go from A to B, and then forced the liquid up. And all this was happening while the temperature was sweeping. Okay, so it's kind of cool. And this just shows you the position of the meniscus versus time, where the time is taking to go from A to B is being measured. You're at A at this point, you're at B at this point. So for the red curve, it takes about 85 seconds to go from A to B. And then as the temperature was swept, these curves were continually measured. And by the time you get to 6.8 C, you are taking almost 200 seconds to go from A to B. And this was a measurement made on water, just to make sure that we could measure data in agreement with the CRC handbook. So the CRC handbook data is in red, and Luc's measurements are shown with all these symbols for a bunch of different runs. So this is one way to measure solution viscosity, and we adopted it because it's what Panasonic uses, and they suggested we do the same thing as that they did. So any questions on this particular method?
One quick question. At the top of the viscometer, so I know that pressurized argon is from the bottom. The top is just open to atmosphere, I assume?
No, we don't open it to atmosphere just because we don't want the electrolyte to react. So.
Sure. So it's kept at a constant pressure, though, I guess, is the crux of my question.
Atmospheric pressure, and it may actually be open to atmosphere. Eric could comment on that.
Okay, thank you.
All right, anyway, so we can measure viscosity, and we have different viscometers available with different diameter capillaries, because if the viscosity gets really large, you'll want to have a bigger capillary so that it can drain in a reasonable time, not in like 4 hours or something. Anyway, so then we come along to something called the advanced electrolyte model. This is something that a guy named Kevin Gehring developed at Idaho National Labs. And when I learned about it, I guess about 6 years ago, I was absolutely blown away, because it's a sort of chemical physics-based model for predicting electrolyte properties, more or less from first principles. So he uses DFT type methods to calculate certain parameters of solvents and salts, and then he models the molecular scale interactions to calculate various electrolyte transport parameters. And he has written several papers on his model. Anyway, we thought, wow, it'll be a lot easier to just calculate things than measuring them. It'll take much less time, provided we can trust this model. So Eric Logan worked together with Kevin Gehring for about 2 years during Eric's master's thesis to really validate the advanced electrolyte model and also find places where it failed. But at this time, the advanced electrolyte model is pretty decent, and I just thought I would show you how it works. And I'm thinking of giving you a homework problem using it, just so that you're aware of its capabilities, because as you go forward in your careers, you may find it important to be able to calculate electrolyte transport properties. So I'm going to change over to the advanced electrolyte model now. What do I have to do? I have to stop sharing this window and then share again a different window. Okay, so hopefully you can see a new window that says welcome to the advanced electrolyte model.
Yep.
Okay, awesome. So we're going to just go through this thing. You can see what it can do. So it says input electrolyte component list and proportions. So what do you want to do? A single fixed composition of solvents. Up to 10 solvents per formulation. So that means you can calculate the transport properties of a very complicated electrolyte system. Up to 10 different solvents. Or you can do a larger matrix of solvent composition for optimization of electrolyte formulation. Okay, so we're going to do a single composition, 1. And it says, for option 1, choose the composition proportionality basis. You can go by volume or by mass. So we'll go by mass, 2. And how many solvents do you want? We'll just pick 2 just to keep this thing simple. And we'll pick, see, so here you have all your solvents that you can select from. So if you look at this list, there's common solvents we are used to: ethylene carbonate, ethyl methyl carbonate, dimethyl carbonate. And then as you go down, you can find methyl acetate in here somewhere. Where is it? Methyl acetate is 29. Lots of different solvents that people use, right? So you can really make a fairly complicated electrolyte blend. Here's fluoroethylene carbonate, propylene carbonate, lots of things. So we'll pick ethylene carbonate, which is solvent 3. And we'll pick dimethyl carbonate, which is solvent 8. Now we have to tell them the mass percentage of solvent 1. We'll pick 30%, because that's typical. EC 30, DMC 70, and 70 for solvent 2. And then it says indicate the number of salts. So you can have 1 or 2 salts. We'll just pick 1. And then it gives you a whole bunch of salts that you can pick from, which are most of the common salts that you would find in lithium-ion cells. And we'll just pick LiPF6, which is number 7. And then it says indicate the maximum total salt concentration of interest, mole-al units, reaching up to 6 to 8 mole-al for battery electrolytes. So it's going to do calculations from 0 molar up to the maximum, whatever you want. So we'll ask for just 3 mol. And then it asks you for the temperature range. Calculated properties over temperature. It's necessary to derive thermodynamic quantities. Specify the minimum and max temperature of interest. Scanning at least 20 degrees C. So we'll go from minus 20 to plus 40, for example. Minus 20 degrees C to plus 40 degrees C. So this is, you know, you can ask Eric Logan about how much easier this is than doing the measurements over this temperature range with all kinds of salt concentrations. Input temperature stepwise in the matrix, and for outputs, we'll go in 10 degree steps. And then it wants you to do some fancy stuff, input method for handling triple ion stability, blah, blah. These really aren't too important. We'll just pick one. Inputs for electrolyte ingress into pores. So you can calculate contact angle if you want. Total pore length. Yeah, I don't know what the contact angle is of this electrolyte that we're talking about. So we'll just pick 50 degrees here. I've never seen this option before. Total pore length. I've never seen this option either. What is going on here? What happened? Where did we get all this stuff? We say 1 molar. Yeah, here we go. And then this option says whether you want surface charge, attenuated electrolyte permittivity calculations are performed. We always say no for this. Double layer calculations are performed. We always say no for that. And then it's starting to calculate. Then it finished already. So do you wish to perform another set of calculations? 0 for no. And then the program ends. So what do you guys see right now? Because I want to show you what some of the outputs look like.
We lost your screen, by the way.
Okay, that's good. That's what was supposed to happen. So let me show you an output here. Oh my, that's crappy. Just trying to get a decent view of this output file. So let me see, how should I open this thing? Normally these files just open up in Notepad, but it's not opening up in Notepad for me automatically. So where the heck is Notepad? Let's try this and see what happens. Oh, here we go. This is much better. Okay, so I'll share my screen with you now because we've got something that's decent. Okay, so I think you should see my screen now. Is it true?
Yep.
You should see a massive table here. Okay, so let's take a look here. So what we've got is results for salt LiPF6 at temperature minus 30 degrees. And it tells you that you've got ethylene carbonate, dimethyl carbonate in a mass fraction of 30 to 70 like we wanted. It tells you the volume fraction of the two, it tells you the mole fraction of the two based on the mass fraction. And then it tells you here the molality in the left column and the molarity in the right column. So if you ever want to convert from molality to molarity, this is a very handy way to do it because the program does very well at this, right? And then it gives you the density, gives you the viscosity, gives you the diffusion constant for the lithium ion, it gives you the conductivity, okay? And all these things for typical electrolytes are very, very trustworthy, as I'll show you in the coming slides, okay? And this is one. This is called report 5 that we've opened up. The program outputs 17 reports, all of which talk about different things about the electrolyte. One of them tells you the percentages of ion pairs, ion triplets, which is useful if you believe in ion pairing or if you don't. You know, here there's some other things. It gives you the lithium ion transport number, T plus, and so forth. And then as you scroll down, you go from temperature to temperature. So now we're at minus 20 degrees. Now we're at 0 degrees, 10 degrees, 20 degrees C. Here's 20 degrees C. So if you wanted results for 20 degrees C at 1 molar, 1 molal, there they are, right? So it's quite incredible. This thing is a really great tool. So everybody should be aware of it if you ever want to do work in the battery space in a serious way. Okay, so I'm going to get out of this. And I'll go back to the PowerPoint now. Okay, can you see my PowerPoint again?
Yep.
Okay. Does anyone have any questions about the advanced electrolyte model?
It's not open source, right?
It is not freeware. You have to pay money to get the advanced electrolyte model. A year license is something like $13,000 US. Okay, so you can use the AEM to explore many aspects of electrolytes. So this just shows the conductivity versus salt molarity at room temperature for sodium PF6 in ECEMC versus LiPF6 in ECEMC. And, you know, people may not appreciate that sodium ion electrolytes have greater conductivity than lithium ion electrolytes, right? I bet nobody listening here knew that. So it means that sodium ion batteries could have an advantage in rate capability over lithium ion when thick electrodes are used. Here's some exploration that Eric Logan did with methyl acetate, okay? So what he's got going on here is mixtures of EC, DMC, methyl acetate. The EC content is always 30%, and the methyl acetate content increases. No methyl acetate is X equals 0, 10%, 20%, 30%, all right? And then he's plotted viscosity versus the molality of the LiPF6 solution. So and these are done at 4 different temperatures shown in the colors. So we look at the top panel, you can see that as the salt concentration increases moving to the right, the viscosity increases. And you can see that as the temperature increases, the viscosity decreases. That's what you expect. The solid points are Eric's data, and the curves are the calculation from the advanced electrolyte model. So you can see the advanced electrolyte model matches the data pretty darn good, right? And you can also tell that as you add methyl acetate from 0 to 30%, like just compare the viscosity curves between the upper left and the lower right panel, the viscosity is reduced by about a factor of 2 at most of the salt concentrations. Okay, so this is why methyl acetate is important for improving electrolyte conductivity. And once you know that you can trust the advanced electrolyte model, you can save yourself a lot of time measuring stuff. So then you can look at conductivity, okay? So again, it's the same matrix of electrolytes with no methyl acetate in the upper left, up to 30% methyl acetate in the lower right. The colors indicate the temperature, and you can see the way that the conductivity increases with temperature, going from like some color that could be, I don't know what it is, pink maybe, up to green. And how the conductivity increases with methyl acetate content. Okay, so any questions about this advanced electrolyte model and what it can do? So just as a point of interest for people trying to make calibrations using NMR, it's pretty difficult to make a very accurate molar solution. But it's very easy to make a very accurate mole-Lal solution. But if you want to make a calibration curve for NMR, you want to plot NMR intensity versus concentration in molar. So you prepare your solutions in mole-Lal, convert to molar using the advanced electrolyte model, and you're in good shape. So people like Saad should find that bit of words useful. And going back to this earlier slide that I showed you where, you know, lithium-ion cells with EMC electrolytes failed at a 2C charge rate. If you add methyl acetate 20% or 40% in red and blue respectively, you can have perfectly fine charging at 2C rates for these thick electrode cells. And this is why you want these low viscosity co-additives in your electrolyte. Now Eric Logan's done a lot of work, and so along with David Hall, to look at electrolyte concentrations with even more methyl acetate. And you pay a lifetime penalty as the methyl acetate content gets extremely high. But you can make some incredibly high, fast charge capable cells with high methyl acetate that still have a reasonable lifetime. And it's really important to note that many lithium-ion power cells on the market contain up to 20% of methyl acetate in their electrolyte. Okay, so now I want to talk about expressions for electrolyte conductivity. So a pretty simple expression for conductivity can be derived assuming the drag force on the migrating ions is given by Stokes' law, which gives you that the conductivity is equal to this simple sum over all the ionic species in the electrolyte. So for our typical electrolytes with lithium plus and PF6 minus, I would range from 1 to 2. 1 for lithium, 2 for PF6 minus. And then there's the charge of the ionic species squared, Faraday's number, the electron charge, the concentration of the ionic species that we're talking about, and then 6 pi. Eta here is the viscosity, and Ri is the Stokes radius of the ion. So the Stokes radius is the effective radius of the ion that's moving through the liquid. So the bigger the radius, the harder it is for the ion to push its way through the viscous solution. And the smaller the radius, so if Ri is small, then the conductivity is big. If the viscosity is small, the conductivity is big. If the concentration is large, the conductivity is big. So this expression matches, what we expect based on just simple logic. And then Kevin Gehring, in one of his papers, talks about how you can effectively calculate something reasonable to use for the Stokes radius in the advanced electrolyte model. And I don't want to go into that detail, just to tell you that, this is an important thing to roughly get right if you're using a theoretical calculation. Yeah, so then Eric Logan made this lovely graph. So if you think about it, conductivity for a particular electrolyte that has the same ions, so the Stokes radii should not vary. If you have lithium plus and PF6 minus, it should be inversely proportional to the viscosity of the solution. So if you plot conductivity versus 1 over viscosity, you should get a straight line at a fixed concentration. Okay, so for a fixed concentration, say 2 molar, you plot conductivity versus 1 over viscosity, and sure enough, a straight line for all these different solvent blends. This is all at 1 temperature. And at 1 molar, you get another straight line behavior, and at half a molar, you get another. Half a mole, you get another behavior, right? Oh yeah, that's not all at 1 temperature. It's at a variety of temperatures. So temperature affects the viscosity. So this is really quite fascinating that it works so amazingly well. And the take-home message is the Stokes radii for the positive and negative ions in the electrolyte is approximately the same over these solvent compositions. So very simple expressions describe how conductivity varies with viscosity, and we'll see in a moment how it varies with concentration too. So I'm going to switch over to my document camera for a second. I think I'd be faster at this by now. Okay, can you see my document camera?
Yep.
Okay, so I want to talk about something called Walden analysis. And again, this is something that Eric Logan brought to the group. And it's described nicely in his master's thesis. So this is the expression I showed you for conductivity a minute ago. Conductivity goes like, I should have the ion type there. Zi squared Fe concentration over 6 pi eta. And I got the summation sign in the wrong place. Anyway, if the ion type is fixed, there's no variation in the ion type, then you can move the summation sign where I had it. And if you then write take the eta over to the left and the concentration over to the left, you get the conductivity times viscosity over the concentration is equal to some constant. You know, the sum over ZIF E over 6 pi and 1 over R is a constant. You're not varying anything in the electrolyte. So that means the conductivity over the concentration, and that's called the molar concentration. It's given the symbol, that thing. So that's called the molar conductivity. The molar conductivity plotted versus 1 over the viscosity should give a straight line. But what is common in this Walden analysis is you take the log of this equation, you take the log of the molar conductivity, and that's equal to the log of this constant plus the log of 1 over the viscosity. And you plot the log of the molar conductivity versus the log of 1 over the viscosity. And if you get a straight line, it tells you that the dissociation of the ions is complete, because you're assuming that everything, if everything is dissociated into single ions, then the molar conductivity will vary in this way. It'll be a straight line. But if some of the ions, if some of the molecules, salt molecules, do not fully dissociate, or if there's ion pairs, then the molar conductivity won't vary the way you expect it to vary. So the Walden analysis is a very good way to look for the presence of ion pairing in your electrolyte. So let's go back to the PowerPoint. Okay, so here's the Walden rule. The conductivity times viscosity over concentration is a constant. And you plot the log of the molar conductivity versus the log of 1 over the viscosity. So Eric's plotted this for the data shown on the previous slide. And all those curves for the different molality end up on a one straight line behavior, okay? So what this means is the amount of dissociation going on in the electrolyte is the same for 2 molar and half molar solutions. So there's no ion pairing going on in this system at all. Okay, so Walden analysis is a good way to take a look and try to understand if you have any ion pairing happening in your electrolyte. And in a few minutes, we'll show an example where the Walden data does not fall along a straight line. Any questions about this?
Hey, Jeff.
Yeah.
I'm guessing the solid line is what the data points should be. So why is everything shifted to the right?
The solid line is just telling you what a slope of 1 looks like.
Oh, okay. So it's not predicting what where the data points should be.
No. Really, if you read about Walden analysis, for a fully dissociated salt, you should fall along this solid line. But if you have incomplete dissociation, you would fall below. But you know, the dissociation in our electrolytes is complete. So that, you know, the reason this is down is just because it is. Okay, so if the data is not parallel to the ideal line, ion pairing is occurring. So all the electrolytes here have roughly the same ionicity, independent of temperature and independent of LiPF6 concentration. So from that, you conclude the drop in conductivity at high concentration is due to viscosity, not ion pairing. So I've talked about that already. Okay, so then we were becoming quite confident we knew what was going on in electrolytes. And then Dae-Jun came along and was starting to work on EC-free electrolytes. And I think Eric measured this data for the concentration of LiPF6, excuse me, for the conductivity of LiPF6 in EMC solutions. It's the blue data here. And if you measure an EC-EMC, you get the red data. And if you remember, I've told you already, that conductivity should increase linearly at low salt concentration, like the red. But the blue does not increase linearly. In fact, it looks like it's almost a parabolic increase at the beginning. You know, so we saw this for the first time and we said, what the hell is going on here? So we thought, let's use the AEM, Advanced Electrolyte Model, to understand what's happening here. So Kevin Gehring keeps revising the Advanced Electrolyte Model as a function of time. And in 2017, when we showed him this data and what the AEM calculated, which is the solid curve, you can see the solid curve is linearly increasing conductivity, and the data is not. So the AEM couldn't capture this at all. And once you see a thing like this, you get really concerned because you wonder what's going on in these calculations. Anyway, so he revised his calculation. Not sure exactly what he did, but anyway, in 2018, he was able to match the conductivity data fairly well with this red dashed curve. Okay, it looks pretty decent. It also captures this nonlinear part at the beginning. So what's happening here? If you take a look at the dielectric constant of the solution as a function of LiPF6 concentration, if you have pure DMC or pure EMC, the dielectric constant of the pure solvent is about 3 or 4. But as you add salt and some of the salt begins to dissolve, the dielectric constant increases. And eventually, the solution can dissolve more salt. So at the beginning, because the dielectric constant is so small, you have tons of ion pairs. Okay, so the ion pairing exists at low concentration in these low dielectric solvents, not at high concentration. And as the concentration increases, the overall dielectric constant improves, and this means the salt can be dissociated, and then you can predict what the conductivity should be. And if you look at other mixtures like EC-DMC, you know, the dielectric constant at the beginning is dominated by the fact that you have EC in the electrolyte. So the salt dissolution is fine at the beginning. So, you know, this was really interesting to us, and it has a lot of consequences if you think that you can use ethylene carbonate-free electrolytes in lithium-ion cells. If you ever end in a situation where you develop a large concentration gradient in the electrolyte, and we're going to learn how this happens, a large lithium-ion concentration gradient in the electrolyte. Once the concentration becomes very small, like 0.3 molar, the conductivity drops to 0, and you'll have a lot of issues in the cell when that happens, right? It's, you know, you don't want the conductivity just going bang to 0 like this, because that's going to create a lot of difficulties in the cell. Okay, so any questions about this sort of strange behavior of low dielectric constant solvents?
Hi, Jeff. So for the LiPF6 dissolved in the DMC alone, what is the solubility of this LiPF6 in DMC? It looks like the solubility is quite good, but considering the dipole moment of DMC is very, very low, how would that be like the LiPF6 can dissolve so much in DMC? So there's no like precipitation occurred at such
No.
low higher concentration. Okay,
No, there's
that's
no
surprising.
precipitation that occurs, and the reason is that as you increase the LiPF6 concentration, the dielectric constant of the solution itself becomes quite decent. You know, it's very similar to that of EC-DMC at that point. The point is at the beginning, it's really low, and the salt dissolves, but does not dissociate well. So the conductivity is incredibly small because you have virtually all the salt, lithium plus and PF6 minus in ion pairs at the beginning.
I see. Also, this only applies to DMC, or this also applies to other linear carbonates like EMC.
Yes, it also applies to EMC. This data here is for EMC on this slide. On this slide, it's for DMC. So EMC and DMC are both similar. So
Okay.
there's an electrolyte that we found in some cells by Samsung. It was 80% DMC, 10% EMC, and 10% EC. So instead of being 1090 like this, it was 10 EC, 80 DMC, and 10 EMC, okay? So it would have started off with a dielectric constant somewhere around 10, and it did not show any strange conductivity versus concentration behavior, okay? It's only when the EC content gets really small, like below 10%, that you start getting into this very strange behavior.
Okay, thank you.
And then if you do the Walden analysis on these electrolytes, okay, so the black line is showing the Walden analysis for EC-DMC 3 to 7. So the little numbers are the molar concentration, or the mole-al concentration. So you can see for EC-DMC, you get a nice straight line. But for LiPF6 and DMC, at the low salt concentrations, the behavior, the molar conductivity becomes incredibly tiny, much smaller than you expect based on the viscosity. And this is because of poor dissociation at low concentration. You know, so these Walden plots are really useful in trying to figure out, you know, what's happening in your electrolyte. And then Kevin Gehring did AEM calculations to plot theoretical Walden plots. And these X's that you see here are the EC content in the electrolyte. So he captures this downturn quite well that we see in experiment. And by 10% EC, like I mentioned, you're pretty much back to normal behavior of a straight line Walden plot, more or less a straight line Walden plot. So, you know, electrolytes are really fascinating, and they're incredibly important. And we've done a lot of work on them in this group, and, you know, scientists all around the world have done a lot of work on electrolytes over the years to try to optimize them for lifetime and rate capability. And it's kind of hard in the end to find, you know, an electrolyte that will promote incredibly high rates and also incredibly long lifetime. And, you know, we got involved in that search, maybe starting 5 or 6 years ago, you know, because we wanted to understand the limitations for fast charge of lithium-ion cells and how electrolytes could be tailored to enable fast charge. Yeah, so this is about to go off into another direction. and it's almost 125. So this is a good place to stop. And I hope that people, that aren't working in the electrolyte space appreciate the importance of electrolytes and the sort of cool things that you can learn about them. I was really fortunate to have Eric do all this work during his master's thesis, because before Eric did this, my knowledge about electrolytes was pretty crappy. But now I feel pretty confident about what goes on in electrolytes.
Jeff, I have a question.
Sure.
Do you expect similar behavior to electrolyte systems that start with a low dielectric constant? So like something that isn't just restricted to DMC or EMC?
Yeah, I think it'll be the same for something like methyl acetate also, which also has a low dielectric constant.
Okay, thanks.
I don't know if Eric's on the call. Is Eric Logan on the call here?
Yeah, I'm here.
Yeah, have you ever measured methyl acetate down to low concentration?
Yeah, so with methyl acetate, you don't see as much of this behavior. I think it has a little bit higher dielectric constant than like EMC or DMC. So even that little boost sort of gets you out of this regime.
Yeah, there you go, Aaron. Any other questions from people? Okay, anyway, so I'm going to start developing homework 5, which will focus on electrolyte systems sort of up to this point. In the past, I have assigned a homework problem using the AEM, where people would come to our lab, sit at our computer, and use the advanced electrolyte model. Now, obviously, with COVID, that can't happen for all of you, but it can happen for students that are in my research group. So I think what I'll do is make a homework that differs for people that are in my research group and people that are not in my research group. And that way, at least some of you will get exposed to the advanced electrolyte model. So, yeah, with all luck, I should get that homework to you by Friday sometime, I would say. All right.